My group searches for a very rare nuclear decay process that will be a smoking gun for the idea that neutrinos are their own antiparticle. So I'm sure that makes sense to everybody here, but since I have more time, let me unpack that statement for you. So when antimatter and matter comes together, they annihilate each other and just give off energy. There's more matter than antimatter in the universe, and that's good for us because we are made out of matter. However, this wasn't always the case. Right after the Big Bang, there was as much matter as antimatter in the universe, but the universe soon became matter-dominated. We don't understand why, but many physicists think that the reason for this may lie in this particle called the neutrino. So the neutrino, just like the electron and the proton, is a fundamental particle. However, they are very tiny, abundant, and very hard to detect. How tiny are they? Well, every second, about 100 billion neutrinos pass through your thumb. How abundant are they? They essentially are the waste from the fusion reaction that power the sun. So they're being made all the time and everywhere. And then how elusive are they? Well, here's a picture of the sun on the left. I'm sorry, well, on my right, viewed through visible light. And then on the left is a picture of the sun viewed through neutrino light. As you can see, this picture is very pixelated. Yet it requires 500 days of exposure time to take it. 500 days. That's because neutrinos are very hard to catch. So how do I study them as a nuclear physicist? I work with a particle called xenon, with an element called xenon. If you wait long enough, xenon, say like a trillion times the age of the universe, xenon will decay into barium, another element, and emit 2 electrons and 2 protons. I'm sorry, two antineutrinos. Now, if the neutrino is the same thing as the antineutrino, then these two will occasionally annihilate each other, and all you'll have is 2 electrons. Our measurements have shown, or have determined that this reaction here on the left is at least 10,000 times more rare than the one on the right. This means that I'm looking for a smoking gun that, if it exists, will occur once every 10 trillion years. That's 1 followed by 25 zeros. So yes, I found the fountain of life, and I'll be here when it happens. Okay. But no, I mean, to be more serious, so essentially, to see this, we need to have a lot of xenon. So what we've done is built a detector that is made out of 200 kilograms of xenon. That's essentially, again, 1 followed by 26 zeros, atoms of xenon. Okay? So then that means that if I'm looking for a decay that happens every 10 trillion years, then now with this much xenon, I should be able to see this thing 10 times a year, right? Not so fast. The energy that's released in those reactions is so tiny that it is very easily drowned out by what we call background or noise. Essentially, that's particles coming down from the sky, raining down on us, and essentially creating signals in our detector. So this is why we have to go down underground and bury our detectors. So we are currently located 2,100 feet underground in New Mexico, in the desert. We've been there for 8 years. We haven't seen the smoking gun yet. And in fact, we know we won't see it because of some detector limitations that are in the current detector. So I'm also part of a collaboration that's designing the next detector, which will be 25 times larger than the current one, and will be buried 6,000 feet underground in Ontario. So the journey is just beginning, and I hope you guys will stay tuned. Thank you.